Okay, let's continue. The last time we got together here was in order to just sort of talk about basic structure. This time we're going to talk about bonding. Bonding is just a, reason why atoms come together. For instance, if there were no bonding between atoms, there wouldn't be any solid matter on Earth or in the universe in general. It's only when atoms start to bond up into big clumps that we call molecules do we actually start to see solid materials. So atoms in general, atoms bond together into molecules. Okay? That's what makes the matter that we see and feel and touch and breathe. If atoms didn't bond with each other, the whole universe would just be gases that you couldn't detect and you wouldn't be around anyway, because you're all, your body is the product of having all of these bonds between atoms too. So first let's go back and review just a little bit. There was one bit of notation that I didn't make a big deal out of yet, and I wanted to make sure that we did that. So let's look at nitrogen. So when I draw this, and there'll be this kind of question on a quiz soon, if I have nitrogen, there's automatically going to be a 7 right there, and then there's going to be nitrogen's mass down there. Okay, so when I draw this in sort of a square box, that's going to be sort of the element and its particles. All right, sometimes I'm going to draw a box, and let's say this one's oxygen. Oxygen is always going to have 8. Usually it will weigh 16. And let's say in this case it's going to have a -2. So if there's a charge on the atom, which makes it an ion, remember, this is an ion because it has a charge. Okay? This is an isotope because it's got a weird mass. Okay? Normally, and I'll show you how you know this later, but normally nitrogen weighs 14. So just quickly as a review, the N stands for nitrogen. The 7 is the atomic number. The atomic number is always the number of protons or positive charges in the nucleus. Okay? The big number is always going to be the mass. Now, regardless if the big number is on the top or the bottom, sometimes you'll see these square units here and they've got the big number at the top. Well, the big number is always going to be the mass. Okay? The mass is always going to be greater than the atomic number. So again, in oxygen, that's the mass. That's the atomic number. Okay? Atomic number is the number of protons. The reason why I'm saying this is an ion is because it has a full charge on it. Okay? Let's talk about what numbers they are. So if I show you this little box and I'll say, okay, well, how many protons are in there? And you'll say, well, all 7, because that's automatically the small number is the number of protons. That's the atomic number. That's also what determines this being nitrogen. 7's always going to be nitrogen. Okay? Let's talk about neutrons. Since protons plus neutrons equal mass, all we have to do is take the proton number away from the mass and we get the neutron number. Okay? So in this case, 13 minus 7 is 6. So there must be 6 neutrons in this particular atom. Okay? 7 and 6 equal 13. That's the mass. All right, so this particular nitrogen has 6 neutrons in it. What that means is, well, it's a little bit lighter than normal. Normal nitrogen weighs 14, which means there would be 7 neutrons in it. So we say, well, this is a light isotope of nitrogen. Okay, a light isotope because it's just a little bit lighter. Most nitrogen weighs 14, which means it's got 7 neutrons in there. All right. Since this has no charge on it, we can assume that the electron number equals proton number, right? Because remember, charge equals proton pluses and electron minuses, and whatever's left over is going to give us a charge. But if there's nothing left over, then protons and electrons are equal. So 7 pluses 7 minuses equals 0. So there's no charge whatsoever. So you can figure out P's, N's, and E's, protons, neutrons, and electrons for each one of those units. Let's do oxygen. So oxygen over here obviously has 8 protons, okay? And then when we're talking about neutrons, well, this is the mass. The mass equals the, where did I write it? Protons plus neutrons. I just take the protons away from the mass and I end up with neutrons, which in this case must be 8. 8 and 8 equals 16 atomic mass units, and that's what we have right there, okay? Now we have to worry about electrons. Electrons are essentially negative charges, and so if we're going to end up with 2 negative leftovers, this is the charge, right? Charge. If this is the charge, then we have to consider, well, what's going to give me 2 leftover negatives when I've already got 8 positives? The way I kind of figure this out graphically is I'll put 8 positives, and then I'll have the negatives here, and then I want to have an overall negative charge. I want a leftover -2 charge. What number of electrons could go right here and give me a leftover -2? Well, I would start with making it neutral. 8 and 8, 0. The only way I'm going to have 2 leftover negatives is if I have 10, right? Because the first 8 are going to get swallowed up. The first 8 are going to be completely negated by the first 8. But then I'm going to have 2 leftovers, and that's going to show. Those 2 charges are going to show. Okay, so I must have 10 electrons in this guy. Let's do another one real quick. Let's say we have sodium. Sodium, I said before, is 11. Sodium usually weighs 22. Okay, so there's my little square. Proton number, 11. Neutron number, well, 11 minus, or 22 minus 11 gives me 11. So out of a 22 atomic unit mass, there's going to be 11 of those neutrons. 11 is 22, right? So it must be 11 neutrons. Now let's deal with the electrons. Remember, the electrons are negative charges. This particular sodium has a +1 charge on it. And so in order to get 1 extra leftover, we've got 11 positives right there, right? That's what that means. And I want to end up with a leftover +1. So I'm going to throw in as many electrons as it takes to have a leftover positive. Imagine that I make this thing neutral. 11 pluses, 11 minuses, right? Well, that's neutral. Well, what is it going to take for me to make this thing a +1? Well, let's take away 1 electron. If I take 1 electron away, that's going to end up with 1 leftover positive charge. Okay, by the way, this is called charge balancing. Charge balancing is a thing that some people have a lot of trouble doing. So this atom is missing 1 electron, and that'll let 1 of these protons show, which gives us a +1. I saw a t-shirt the other day that said, "I'm positive I lost an electron." There's a picture of an atom. So if an atom that's neutral loses 1 electron, it becomes positive. Okay, let's just do charge balance just for a second. If I have 14 pluses and 12 minuses, what's the overall charge? Well, there's 2 left over, right? This is going to show 2 of those. If I have 1 positive and 3 negatives, I have 2 left over. 2 negatives are going to show, right? Because I'm only getting rid of 1 of those. So it's whatever's left over and how many there are left over, all right? If I have 11 positive protons and I have 5 negative electrons, what do I have? That's 6 positives are left over. Does that make sense? 6 positives are left over because only 5 of those are going to get sort of negated or canceled out. You should practice that. We'll do one more. So 14 positives, 13 negatives, +1, right? 6 positives, 8 negatives, -2. 2 of those are left over. All right? It's as easy as that. All right. Now let's go specifically to bonding. Bonding is essentially a result of atoms being unstable. Atoms bond to each other in order to become stable. Stability is basically what chemistry is all about. All atoms, well, nearly all atoms have kind of a bad number, a crappy number of protons, and so then they have to deal with that for the rest of time. They have to deal with the fact that they don't have an ideal situation. And that has to do with the electron shells that we talked about, and we'll talk about a little bit of stability rules now. So there are two general rules of atomic stability. And every atom has to try constantly to try to satisfy these two rules. I'm going to put them in order of importance, not necessarily in time, but importance. The first major rule, and this is the one that has to always be true, and this is what causes chemistry to happen for the most part. The outer shell, the outer electron shell must be full. And what do I mean by full? Well, the first one has to have 2, the next one has to have 8, and the third one, if you need it, has to have 8. So whichever shell is on its way to being filled, you've got to take care of that. And every atom is going to spend its entire time here in the universe trying to fill up its outer shell, one way or another. It may not be perfect, and many atoms change direction all the time under different circumstances. One atom might change partners in order to satisfy itself under the new environment. The outside shell is called the valence shell. The valence shell is the shell that must be full. It's the one that's nearest being full right now. And we'll talk about that in a second. Second rule, almost as important, although many atoms can cheat this deal. The second rule is that there must be a minimum. There must be a minimum of overall charge. And by minimum, it's kind of a sliding scale depending on the element, but a minimum means like a -1 or a +1, that kind of thing. There are a few atoms that can get away with having a +2 or a -2. Those are metals, and we'll talk about those a little bit later. But in general, a minimum is a relatively small number of full charge, okay? And we'll deal with that along the way. Okay, so those are the rules. Remember these two rules. These are super important. This is what's going to cause bonding. All of chemistry, and this is non-nuclear chemistry. This is the chemistry that happens in order to make life happen and geology happen and that sort of thing. All of chemistry is about atoms trying to satisfy or solving those rules. Because under one circumstance, an atom of oxygen, let's say, may have a full outer shell, but then you heat it up a little bit, and it may not be stable like that, and it may trade partners and fill up its shell with somebody else's electrons. And so that's chemistry. When electrons trade partners and they bond with certain different kinds of things, then we call that chemistry. All right. Okay, so let's talk about the different kinds of cheats, different ways that we can solve these two things. Let's see, shells can be filled in basically 3 different ways. One, stealing electrons. Okay, is that how you spell stealing? No idea. Let's say that's stealing. Stealing electrons means that you're going to become negative. Okay, because let's say you're already neutral, and then you steal an electron from somewhere. Well, now you're adding up your negative charge, and I'll show you that graphically in a second. The second way is by losing electrons. Somebody else steals them. Losing electrons means that you're going to become positive. I'm positive I just lost an atom or an electron, right? The third way, which is the best way, but not all atoms can do it, is by sharing. If you share electrons, you don't get any new charge. And this is why it's ideal, because you can fill up your outer shell and still not have that charge, because the second rule is you got to have a minimum of charge, right? So first one, fill out your outer shell. Second one, now look and see if you've got a charge, and then you have to deal with that in another way. That's kind of a cheat, all right? So let's first deal with, well, let's just put sodium here and chlorine over here, all right? This is the easiest one. So I've got chlorine atom, I've got a sodium atom. First of all, the first thing you're always going to do to figure out what kind of chemistry is going to happen is make the thing neutral. So 17 protons means I have 2 there, I have 8 there, and I've got 7 more right there, right? 287. And then we call that the electron configuration of chlorine, 287. Okay, that's 17 electrons. Sodium, on the other hand, 1 shell, 2 shell, 3 shell. It's got 2 here, because I've got 11 positives, right? 2, 8, that's 10, 1. 281, that's the electron configuration of sodium. Now, neither one of these atoms are stable at all. Neither one of these atoms are going to stay this way for more than a tiny, tiny little fraction of a second, right? They have to make sure that they have a full outer shell. And once they have a full outer shell, then they have to deal with their newfound charge. So these two are perfectly suitable for sort of taking care of each other's charge. Sodium would love to get rid of this because this is a shell that needs 8, but it's only got 1 on it. It can't steal 7. There's just no way, because there's no way it would grab onto 7 extra electrons when it's already neutral. On the other hand, chlorine would love to fill up its outer shell with 8, which it needs, right? Where's that piece of paper? So the shells go something like this, 2, 8, 8, right? Well, this one's got 2, 8, 1. That's horrible. This one's got 2, 8, 7. That's so close. And so what's going to happen is the chlorine is going to snag this one from sodium. That's going to leave this one missing an electron, but now this one's got an extra. All right, super weird. So in other words, chlorine now has 17 positives, and it's got 18 negatives. 8, 9, 10 plus 8 is 18 negatives. That gives this thing a what charge? -1 charge. So now this is chlorine -1. Ionic chlorine. So chlorine is almost always a -1. Sodium, on the other hand, now only has 10 electrons. It just lost that one, right? So it has 11 positives right there, and it's got 10 negatives because it lost the outside one, and now it's got a what charge? A +1 charge. Okay? So now I have a sodium, +1. I have a chlorine, -1. And these things now have another problem, right? Sure, they filled up their outer shells. This one filled it up by getting rid of one, and now it's got a full outer shell. This one filled it up by stealing one, and now it's got a full outer shell. But there's a problem. It's got a full outer shell, but now we have to drop down and deal with rule number 2. These atoms have to get a minimum of charge. Yes, 1's not bad. 1 plus and 1 minus isn't bad, but you can sort of cheat this and get rid of that charge altogether in a virtual sense. If these stick like magnets, if pluses and minuses stick together super close, you can't feel the charge at all. The charge goes away because they're so close that those two charges sort of take care of each other and they stick. This is called sodium chloride. This is what table salt is made out of. The reason why we have table salt is because chlorine usually grabs an electron, becomes negative. Sodium typically loses an electron and becomes positive, and then they find each other. And when they find each other, You get NaCl. It's called sodium chloride or table salt. These things are being held by what's called an ionic bond. An ionic bond is when two atoms stick to each other because they have opposite charges because they're ions. They're opposite ions. Okay? So I'll write that down formally. Types of bonds. Types of bonds. Let's first talk about ionic bonds. Ionic bonds basically happen when two atoms of opposite charge attract and stick to each other. All right, that is an ionic bond. There's all kinds of ionic bonds, right? I mean, anything that has an opposite charge can stick. So, for instance, you can make sodium chloride. Magnesium has a +2, and chlorine, like I said, usually is a -2 because it usually, I'm sorry, a -1 because it usually steals one. Magnesium usually loses 2. And so when these things stick, magnesium sticks to chlorine, except you need 2 chlorines because chlorine only has a -1. And so it's going to take 2 chlorines to actually get rid of this. So really what happens is if you have magnesium with a chlorine on either side, and that takes care of that 2 negative or that 2 positive charge. We call that magnesium chloride. Magnesium chloride is another salt that we use for, in some cases, melting snow and ice and that kind of thing. All right, these are called ionic bonds, when 2 atoms of opposite charge. And the reason why they have charges in the first place is because they're trying to fill up their outer shell, right? Rule number 1. All right, let's talk about the other kind of bond. The other kind of bond is the most important one for making you and solid matter that we know of, and that's called covalent bonds. Covalent bonds are stronger. They're more consistently held together. For instance, ionic bonds oftentimes are disrupted or broken by water because water is kind of charged, and so they tend to break apart. That's why you can dissolve salt in water, and water gets in between these bonds. Well, this other kind of bond, you're not going to see that happen. Covalent bonds work so well to satisfy both rules. Covalent bonds are going to solve both problems at once. They typically don't get disrupted unless there's some sort of energy source from the outside or some major reason why these bonds would be stabler in another configuration. So a covalent bond essentially is this. When 2 atoms share, that looks like shave, but it's share a pair of electrons. Which then orbit both. And this is the cool thing. This is going to you're going to fill up your outer shell, but the atoms aren't going to get any extra charge because you're not going to strip electrons. You're not going to lose or gain electrons. You're just going to share the ones you've already got. Okay? So when 2 atoms share a pair of electrons, which then orbit both nuclei at the same time. It's sort of the ultimate cheat when we're talking about the rules. We're going to cheat this and fill up the outer shell, but we're going to cheat this because we're not going to end up with a charge at the end. So let's just talk about oxygen for a second. So oxygen is number 8, right? Typically it weighs about 16, so it's got 8 protons and 8 neutrons under normal, a normal neutral oxygen atom. If I were to make oxygen neutral, it would have 2 here, and then it would have 6 here, and that would be 6, 7, 8 positives, or I'm sorry, 8 negatives and 8 positives, and that's neutral, right? That's my normal neutral oxygen atom. Well, that's a problem. Oxygen has to have a full outer shell. Oxygen has to fill that second shell up with 8, right? Well, it's not that far away. It only needs 2 more. Oxygen's tendency is to steal 2. Although, if it did steal 2, it would then be oxygen -2, which really doesn't count for a minimum of charge under most circumstances. All right? So oxygen then is going to have to do something different. It's not generally going to steal electrons, it's generally going to share them with somebody else. And I could pick almost anybody, but I'm going to pick on hydrogen. I'm going to put a hydrogen right here and just draw it. So hydrogen has one proton. It generally doesn't have a neutron, so it usually weighs one as well. I'm going to put another hydrogen over here. And this hydrogen is the same. Hydrogen weighs one proton. It usually doesn't have any neutrons, and so it weighs one as well. All right? So in order to make this neutral, I put one electron right there. Right? And in order to make this one neutral, I'm going to put one electron right there. Okay, so I have a very unstable hydrogen, a very unstable oxygen, and another very unstable. Why is it unstable? They don't have a full shell. Neither one of these, all three of these atoms have an unfilled valence shell. For instance, this one needs one more. Hydrogen has to fill that one up with two. This hydrogen has to fill this shell up with two. This one needs two more to share, right? So if I have this shell and these electrons are going around and 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 around, very, very, very quick around this orbit. Imagine if these got close enough, these atoms got close enough to each other that this electron started to also orbit this shell. And this electron got close enough where it started to orbit this shell. Imagine that one of these 6 started to orbit that shell at the exact same time, okay? And one of these 6 from this shell started to orbit that shell at the exact same time. Well, if this were to happen, I would have at any one time, there wouldn't be 2 electrons, but for the entire time, this would have 2. So now, hydrogen in a virtual sense has 2 electrons flying around it because it's sharing that one and 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 that one. At any one time, this one's headed out and this one's headed back, so you don't gain any charge. Same thing here. As this one heads towards the oxygen, this one from the oxygen is heading toward the hydrogen, so there's no charge overall. At any time, however, if you were to count the virtual number of electrons between them, there's 2 here, that's a full outer shell. There's 2 here, that's a full outer shell. Now let's look at oxygen. In a virtual sense, oxygen now has its 6 plus this one and plus this one. That's 8, right? And so now oxygen, in a virtual sense, has 8 in its outer shell. Check it out what we just made. We made oxygen and hydrogen bond together, sharing an electron pair. Oxygen and hydrogen sharing an electron pair. That's called H2O. The only reason why water exists is because this particular makeup, this configuration, this satisfies everybody at once. Everybody has a full outer shell. This guy's got a full outer shell. This guy's got a full outer shell. Everybody's satisfied. There's no charge. There's no overall full charge because we haven't added or subtracted any electrons. Everybody started out neutral. Everybody's still neutral. Okay? This is what's called a covalent bond. A covalent bond is when pairs of electrons are shared in order to fill up your shell, and you don't get any charge as a result. So in other words, you're sort of cheating both things. You fill up your outer shell, you don't get a charge, everybody's good, and you don't have to be unstable anymore. Okay? So in other words, all molecules, let me just write this here, all true molecules are sharing electron pairs in order to solve both stability rules at once. Let's look at one more. Let's just give one more and then I'll let you go. So let me pick out another one. Nitrogen is always 7. It almost always weighs 14. So here's my nitrogen. Nitrogen is never stable. I'm just going to pick on hydrogen again because hydrogen's an easy molecule to play with because it only needs 1. Right? Hydrogen only needs 1. So hydrogen has 1 electron out here, 1 electron out here, 1 electron out here because it's number 1. Nitrogen, on the other hand, has 2 in the inner shell, And then in order for nitrogen to be neutral, how many does it need out here? Well, it's got 2 already, and I'm going to put the other electrons, the other 5 out here. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7. That's neutral. Nitrogen is now neutral. Nitrogen hates being like this and won't stay this way for very long because it doesn't have a full outer shell. That shell needs 8 in it, and right now it's only got 5. So it has what's called a valence of 5. Hydrogen needs 2. It has a valence of 1. Okay? How are we going to solve this? Well, if that electron heads that way and this electron heads that way, now hydrogen's good. It's got a full outer shell. If this electron heads this way and this electron heads this way, that hydrogen's good. It's got 2. It's got full outer shell. If this electron heads that way and this one will heads that way, now that one's good. Now, let's look at nitrogen. If all the hydrogens have a full outer shell with 2, this nitrogen in a virtual sense now has 1, 2, 3, 4, 5, 6, 7, 8 full outer shell. The only reason why this molecule exists, this is called ammonia. You've heard of ammonia. The only reason why there is ammonia anywhere is because it takes care of everybody's valence needs. Your valence needs are what you need to fill up your outer shell. And this configuration, NH3, takes care of everybody. This is a molecule made out of nitrogen and 3 hydrogens. And that's a case of covalency. Covalent bonding makes molecules. All right? And we'll talk a little bit more later about some of the weird things that happen as a result of that.